Hi everyone, thank you for being here today with us. So I'm Manuel Serrano. I have been organizing or chairing this workshop this year. So it's a 10th edition of REBLS, so already pretty old. So it's glad to be active and productive. So this year, maybe we have received slightly less submissions than previous years, and I think we have been fighting against, or we have been struggling with the deadlines, which were not so convenient. Just middle of summer, it's really inappropriate. So I guess that for the following year, we will try to improve on that. But anyway, all the submissions we have received were quite in the focus of this workshop, so quite interesting, and presenting interesting ideas. So clearly, we have received little numbers of submissions, but all were interesting and probably engaging interesting discussion. So this is why probably we will have an interesting workshop. And once again, I welcome you here in Portugal and for this workshop. So thank you so much.
Greetings, Rebels. Welcome to the first session. So I will be another piece of furniture that you will encounter today. I'm the session chair for the first one. So we start, of course, with a keynote, and the keynote today is Elisa, and it is my utter pleasure to introduce her. So Elisa Gonzalez Boix, she's a professor in Belgium, in the Free University of Brussels, and she has been repeatedly publishing on exactly this topic of, agent-based reactive system. So if you've never heard of her, then well, probably listen first to the keynote, but then do Google her up or DBLP her up, because she has written quite some interesting pieces on this topic. And she's also head of the DISCO group, which is about distribution and concurrency. Thank you very much. So the floor is yours, and do your thing.
Yeah. Okay, so this is a workshop, so you can interrupt me at any time and ask me questions. I will try to do a brief idea of what I have been working with my group in the DISCO, and I will do two zoom in so that I don't bother you with all the details. But let me explain you a bit how it all started, and I see the slides, good. And it all started 20 years ago, yeah, that's how old I am. In computer science, and I was I'm originally from Barcelona, Universitat Politécnica Catalunya, and I went to Brussels to basically do some research for my master thesis about basically a programming model for ubiquitous computing. That was something big by then. It was this vision of Mark Weiser that has postulated earlier before, but now the hardware was getting there that we could start looking into how to really build software for those systems. So my supervisor then, my master thesis supervisor said, in an ubiquitous context, actually asynchronous communication suits better. Why do you don't implement an actor-based language? And I was like, a language? Seriously? So I come from a systems background, so I had always been programming in C, looking at databases, networking, and I had not even considered the fact that I could become designer of a language. I mean, that was mind-blowing for me, a different philosophy there than where I came from. So my own language, I guess that with the 4-5 months that I had to be there, he kind of knew that maybe it was a bit overwhelming. I had only written a compiler before for a course. So then he said but we have a couple of people running around in the lab, which are already taking a small language that we have for education called Pico from later my supervisor, Theodon, and trying to put it into, re-implement it in Java, because there is this promise that then you could run anywhere, including wireless communicating devices. And so that's when basically I first learned about the language. It was a continuous in-passing style interpreter written in Java. There were a couple of people looking into writing communication for this based on SOAP, some technology of objects over web. And my supervisor said, read this paper about Gul Aga and try to see if you could basically merge this into the objects of Java Pico. And that's how I ended with my master thesis. I looked it up, and I'm not very proud of the syntax or how it looks like, but it was my first attempt at working in basically building a programming language or a programming model for Wiki2G's context. And then, yeah, it was not really evident to me that I could live from doing research. I had a wonderful time, but how do I get food? And I couldn't find a job in Belgium because I didn't speak Dutch. I spoke French, but not good enough to be hired. So I went back, and I went back to my system programming. So I was working from UPC, developing tools for IBM DB2 on those days. But yeah, there was something in me that made that holidays, talking to people, make me start it all over again. So here we are, a year and a half later. I come back 2005, but there is not like 2 master students. They already have a group. And my supervisor, Theodon, with them, like brainstorm, like what can she be looking in within the same topic. By then they had developed ambient talk built on those ideas, and it's like also an actor-based language. They already had a full-blown distributed model. It's like, what about if you explore how to handle failures there in ambient talk? And I was like, ambient talk? What's that? It's like, well, this project grew. We found some Catalan code comments, very bad. You should always write in English. It's like, wait a second. Till now, I still have not found this code. I tried for this presentation, but I did not find. So I think it's not true, but okay. So I joined the group, and then I started basically looking into how we could model failures in an object-oriented way, because we were trying to program distributed applications. We were very dynamic. So you were peer-to-peer, you will meet on the devices, and then start collaborating. So ambient talk, they had been working on marrying events with objects. That's what they were doing. And it was a superset, so it was based on the principles of ambient-oriented programming. You have a superset of object-oriented programming, which is specifically geared for distributed computing, but especially for these mobile networks. Why they were so special? Because it didn't have any infrastructure, fully decentralized, and there were a lot of failures. So by then it was a bit niche, but by now, like having decentralization and having to deal with failures, it's quite normal, not only in mobile networks, but in any modern distributed system you encounter, from cloud to IoT. So, okay, if you look at the programming model, you had to basically discover services and ask application requests, and that will be modeled with asynchronous message passing, which have a special operator. You know that in Scala they use like as well special operators. On Erlang, this was the one for us in ambient talk. You will also have events to follow up on your request. So if you sent an asynchronous message, you wanted to get the return value, again, there was an event model, the resolution of a future. Some of you might know it as promises. And then you would apply a closure when this event happened. And then we had events to react to the fact that we were in an ad hoc environment. So discovering services, whenever discover, you get a reference, so object reference to another device, or reconnecting and disconnecting when you lose network failures. So to give you a feeling of how this look like, this is a little ping pong application. So on the left-hand side, you have a phone in which it's exporting an object that has a ping method. So when it receives that request for the ping, it will write ping on the console and send back the symbol pong. And this object could be exported with what we call a type tag. So think about it as an empty Java interface. And then that makes that you will put it on the network. So basically, the language had facilities like PubSub built in. At the other side, what you have is like, okay, you define the same type. And whenever you discover this type tag, then this closure will be applied, and you will get an object reference to that device there. So then you could start doing like requesting services like the ping. I want that it's a future message, because when I get the value, I then received the ping. So in this model, basically what we had, it was clearly event-based. You have all these callbacks for different types of events. And the data was stored at an owner. So in this case, there was this object, ping pong object. And all operations will happen via synchronous message passing. That was good. It decouples devices. It allows you to build things. But all operations will be executed, let's say, at the owner. So I was trying to reconcile then failures and their effects. And that's where one of the things that I did that are in the trunk of the language, it's basically integrated with leasing. That allowed me to solve two problems, because on these references that we had here, it allowed me to basically do some cleanup. I could say, like, for 10 minutes, this connection is valid. And after this time, I can do some garbage collection at this site. And at that site, the sender of the request will be able to distinguish between intermittent and permanent failures, when is a connection needs to be considered that you would drop. And that's what they did. So we integrate the failures in the model so that it will be a bit easier for the programmer. So that's how your references now from objects in different machines will look like, from connected to disconnected to reconnected, and sometimes we will just cut them when they expire, and from here on they are useless. So there is a new type of event coming in, the expiration, very important at that site to do garbage collection. Whenever this object is no longer locally referenced, and very important, it could be triggered at that site to react to permanent failures. Basically, that was the idea. So that was part of my PhD. And then I procrastinated a lot. I don't know if that's allowed nowadays in programs, but what does it mean, procrastination, since the very beginning? Well, we wanted to build things, right? There were all these devices. At the beginning, the devices were just laptops. And the demos like there, you don't see it a lot, but it's a Portal game. The performance was not our goal, but it was quite horrible. I had to animate the demo, so we record the demo. And then with the movie, I had to animate it because otherwise the ball was so slow that it was embarrassing. But it's distributed, right? So a ball could go from my device to there. We'll be jumping around. Then luckily for us, in 2009, nicer devices come, easier to basically target them than just having a Java VM with Android. So then we could really start thinking about more application case. So it was a lot of fun to, on Fridays, have these hacking sessions. Then we also had supervisors giving us money to buy devices. That's also important. We had money to buy devices. So I started going with some of my colleagues to hackathons. This is like distributed paint drawing. This is a Pong, a real one, so not this one. You can play it, and my students are still implementing this as an exercise now at class. Pong, that they pay us to go to London to continue programming on it. So, and when you are building all these applications, actually we had built a model with objects and events, where the main abstraction when these object references crossing devices. But I realized actually that in many times, what I needed to implement these applications was to share data. And basically, this is another example. Imagine an imaginary country where they want to do elections, called Catalonia, doesn't exist yet. And then you want to build this voting system where you want to represent basically what's going on. In ambient talk, we had objects were passed by reference, but you could also have something called an isolate. And an isolate will be an object that was passed by copy without its lexical scope. So then basically that was interesting, because from a point of view of the model, that means that you could do operations execute locally that will faster, so it will increase the availability. And also you could have different copies, replicas, so increase, like you avoid a single point of failure of a reference where you always need to go to the owner of the data, right? But the problem is that, consistency was left up to the programmer, because rather than building it in, it was by design that we will always try to be available and partitional tolerant. And if you know a bit about distributed systems, there is this big famous theorem called the CAP theorem that says that you cannot have availability, partitional tolerance, and consistency. So at this moment, consistency was left to you. So every application, you will have to basically build it over and over. And that's when it's like, well, but we could build some basically replicated objects, right? And what do I want? I want abstraction that developers can customize conflict resolution. Because if you have replicated objects and you have concurrent updates, you will need to deal with what do you do when they are conflicting operations or updates. And here is like my supervisor, like had already talked to me or given to me at some point a paper called the Boix architecture, support for data sharing among mobile users. And this was a paper by Demer in the context of actually more like the mobile adult networks kind of world, okay? But in the databases kind of community. But I found this very interesting because I'm sorry that the font size maybe is not big enough for the back. But basically what Boix allowed is that you could have like a number of database services that you could connect from different locations because the users were mobile. And then you could always issue an update. And with an update, this is an example from the paper, so very old, it's from '95. It says I want to do a meeting between 10 and 60 minutes for project meeting with Kevin. And then it had this dependencies check that actually was kind of checking if the update will be, what are the conditions so that the update can succeed. So basically, it will select the key from the meetings table to know that there was no other meeting already there. So the result, the expected result, the expected invariant of the application was to be that this will be empty, so that then you could add this record. The thing is, like, if there will be a concurrent update and there will be a problem and this doesn't hold, you could have a merge procedure that will try to give the means to the developer to resolve this conflict. And here, basically, it is still, as I said, it's in the databases. It is expressed in terms of SQL queries. So it will check there's a conflict, and if not, select another time. And if don't, give the bug this time. Otherwise, it will have to retry. So this is very interesting because I have application-specific, basically, conflict resolution. But I didn't like that you are exposing these merge procedures directly because they are very difficult to get right. And you also need to ensure that then the two replicas will converge. So it's like, yes, I want something like this, but I don't want the explicit merge. And that's why when basically there were a group of people that they had already been thinking about that. And I found super cool the work of Shapiro et al. From CRDTs that came in 2011, because here, behind the abstraction, they will, for a number of data types, they will already give you by default a merge procedure. So you as a programmer can basically get a data type, and then the implementation takes care by design following some mathematical properties that you couldn't have the conflicts. So that's nice. I thought this is a nice abstraction to give to the programmer. Basically, they had already some work out all the merge procedures for a number of data types. There were flags, there were sets, there were registers, there were a number of data types there. Okay, cool. So this is a specification, for example, of what it's called a state-based increment-only counter. So what I would need for my voting system of my imaginary country. And then basically this is how it would look like in ambient talk. So you would, you don't need to know a lot about the specification, but basically it's using a vector of increments on every position will keep the increments of every node in basically that it's participating in, or every replica in the network. And then when you increment, you actually increment the position of your ID on that vector. So when you merge, basically what you are doing is taking the maximum for so the vector that comes to you from the network from the one that you have. Okay, that's nice. This paper didn't talk anything about the distributed aspects. I want to use this in distribution, but okay, it's good. I know how to do that. We know from ambient talk. So basically I can just like put in the distributed aspects, and how would we do that in ambient talk? You will define a trait, an object, where you basically will pair everything that you need to discover the replicas and what to do when they are not online and so on. That is something based on the event-based model of ambient talk that we could already quickly hack in. And that's what is going on here, right? So when you want replicas to sync, this is the sync method usually from that you will propagate the update. So it just does a broadcast of the merge function getting your own information. So serializing will mean to send over this vector. Broadcasting Well, I just had to keep basically a connection to all replicas. And how do you model this in ambient talk would be an object reference that I will use like the same kind of events. I will export self so that everybody can find this replica. And whenever I will find a replica with the same name, then I will just add it in my list. That's needed so that then at every broadcast message, I can just forward the message. That's what you see here. There was a lot in this ambient talk language, like reflecting was built in. So basically, this wasn't a special operator because messages were first class to then say, this message I get here, send it to the receiver, which will be in another machine. That's nice because I have my RDT, and by importing the trait, I get my distribution, basically. But I was not done, right? Because basically, I have a number of data types, but they are not application specific. I have sets, I have registers, I have counters, I have a number of them. And there was a lot of people thinking about how to design these merge procedures, or there was also like how to make operations commute if you take another branch of CRDTs, so that you can offer it as an abstraction, but you cannot customize the concurrent semantics to your application. You always need to take a different data type. And if you don't have a data type, either you create it or you wait that there is another PhD student who comes up with the tricks. So that's one thing. The second thing is like, I want to support application invariance. So some of these, it's not only about that the state converges, sometimes you also need to uphold some invariance, and this might transcend one data type. Second thing is like when you don't have a CRDT ready to go and you start building, how does the developer know that it's correct? So in this sense, correctness a lot of times is associated with converge. So how do you know that it will eventually, all the replicas will be in the same state? Because yeah, for the CRDTs, there is a lot of smart people who have already worked out the proofs. So they publish the paper with a manual proof, or in the old days, now it's going more mechanized. And they know that this is correct. But the moment that you start extending it and making it to your application, you need to provide some means of how are we going to make that the programmer can be sure that its modified design is still correct. Composition. So if you think about object orientation, you always immediately think about having composition by means of nesting objects, etc. And this was also like, how I am going to do this with these replicated data types. And finally, because I always keep the touch with the hardware, I was looking as well to more Internet of Things applications. This one ran on low memory, low power devices. So how do I feed this nice research, which is meant for geo-distribution, into environments which are dynamic, like I had with the mobile networks, but that they are memory and network constrained? So there are a lot of questions that I have been looking with my group. And then what I will do is to zoom into one of these questions, because obviously I cannot start here, like going over all. There is a lot, and some of these questions we are still working, our group and also the community. Okay, I will do a pause for drinking. I don't know if there is something already on the ambient talk part before I delve into the first zoom in with the replicated data types.
What is left of all the things you have done with ambient talk? Is it still active? Is it,
I use it for teaching, distributed programming. Many of the things that I use the language as a vehicle to basically bring on the concepts that are now being in research or that they are established. But it's like a vehicle now for teaching.
And the core concept of this language, have they been reused in other programs?
Well, so there are some aspects of the language that have percolated. For example, there was a lot of work on the reflection aspects, so that you could change the language within the language, because we needed this. There were a group of students, and each working on a topic. So what you want is a small core that then you can adapt for all these experiments. And for example, this line, then with Tom Van Kutsem working with Mark Miller, got into the ECMAScript proxies. So actually the mirrors, intersection mirrors of ambient talk are now like applied
Inspired the proxy thing.
to the proxies. Yes. So this is one of the most successful transfers that there is within all the basically research within because it was a big group. I think that we were about 10. At some point, there have been, I think, 10 PhDs being produced, but Wolf is not here, so he probably keeps account. I was only exploring failures, so I talk about my side, but there were many people there, including Christoph, which is also here, and you already saw his hand on the phone. Okay, so let me do the delve in then. I want to talk to you about this quest to have this basically general abstraction, because I want to keep into account the application semantics. And this is basically work that I started with my PhD, Kevin, and at some point we ended up going to Carla and Nuno to join forces to get this, basically to help us get it streamed out, and we collaborated with them for a couple of years on this. So the idea is like you want to invite these new data types for your application, but following the mathematical properties of CRDT sometimes is very hard. And we also, or personally, I also didn't know what can you express, or that as a CRDT, what kind of things will be able to be expressed as CRDT, and which ones we will not be able to find tricks so that basically the state converge. That was the idea. I want to have built any data type, so go more general purpose, taking into account application semantics, but trying to remain basically available as CRDTs. And that's how we came into the explicit, consistent, replicated objects. So the idea was to build a general purpose RDT. Initially, that could be like CRDT. So basically, they provide state conversions. But I didn't want to give directly RDT. I wanted to start with a sequential data type, because that's well understood for programmers. We all have this in computer science. And then, like with the idea of Bayou, it's like, what if we could add a distributed specification that will say how does the sequential data type has to behave when they are concurrent updates on the operations. That was the idea. And then I want to get back a replicated data type, which as much as possible avoids having coordination. That's what CRDTs do. You can update them offline. They have a built-in conflict resolution mechanism that does not rely that all the replicas have to be online to agree on a value, which is the old way of doing it with the databases and a strong consistency. But yeah, there are times that it could be that that basically that's not possible. And when it is not possible to avoid coordination, then we will go into using logs. So it's a hybrid data type, because the idea was that you want to provide an abstraction that basically hides as much as possible as the difficulties of resolving conflicts. That's the idea. Okay. Oops. So we move from ambient talk, dynamically typed language, inspired a lot by Smalltalk, Lisp, the E language, Self, etc. And we go into a Scala. So basically, that's my fault. I said, I think that the Scala for this kind of work could be better than Erlang, what he wanted to do. And then he went to Scala, full types started falling. I have learned a lot about this. So what do we have? We have a sequential data type, here written in Scala. We will have a domain-specific language that will help us, written in Scala, will help us with this distributed specification. So the SALT, to say what are the concurrent semantics that this application needs. And then we get a replicated data type. Let me go over the two components so that you understand what is the idea. So first, if you want to do something like an add-wins set, that's a well-known CRDT. It's a set in which if you have a concurrent add and a concurrent remove, the add will win over the remove, because the thing is like they don't commute, so one of the two will have to win. So you have a sequential implementation. In Scala, you basically leverage into the data types that the Scala had. Like I said, you need to provide the adds that just as it provides you a new set with the element. The remove will remove it, and then it checks the contain. So basically, it's quite close still. The idea is to remain quite close as possible, as close as possible as to the specifications of CRDTs, while being a real language implementation. And then there will be the distributed specification. What does this mean? Well, what you see here is a small DLS on top of Scala. First of all, what I want is that I will have to specify what are the effects of each operation, and that was done inside the post condition. So the post condition of add will take the old state and the new state. It will check if the element is in the new state after you do an add. We need this relation. I forgot to say it. And then, it has to do a copy of the old one to check that it is that it's the only element that remains there. And then you have the post condition of remove, which basically will be the opposite. It should not be there, and then check in the copy set. Well, you see, this is the domain-specific thing. This will be an AND. He leveraged it on using a Scala meta. And the important part for us is here, because that just is telling the effects of the operation, but the invariant is what will define the concurrency semantics. And that means it's an invariant on the add operation, and then after checking all concurrent operations with that, what needs to happen is that the element is still in the set. So if you would have a concurrent remove, when this invariant comes, then you had to make sure that this is done. So what's going on here? You start with a sequential implementation, and you add an invariant to express basically an add wins. If you want to remove wins, I don't need to go and create another data set. I don't change my sequential implementation, but I need to change my invariant. I don't want that it's an invariant on the add operation. I want it on the remove. And in this case, after checking all concurrent operations, the element should not be there. So if there was a concurrent add, the concurrent add should lose. That's basically the idea. Are you still all with me? Because that CRDT is going, phew, okay? I know that maybe some of you are not in the data. Yes?
Yeah, I'm not totally following, because what I see on the left-hand side is something rather abstract, so just describe you a kind of interface, but no implementation details, because I don't know what is behind this.
Yeah. Yes, this is a wrapper actually around this that will then have the conflict, the algorithm for the replication.
But where is implemented the algorithm? In the semantics of the operators, of the plus, minus?
No, it's on the wrapper. Then it's on the wrapper imports basically the acro algorithm. It comes in a couple of minutes.
Okay, and the thing on the right hand side, it's just a kind of an assertion, or is it producing some code, or what?
Yeah, it produces some code about that, some basically forma or logic or formulas that we then will dispatch to Z3 to check that that's upheld. Yes. Okay. So it's basically logic, first order logic, what you are kind of writing, yes.
So you use this for static
analysis.
And saying that yes, your implementation is correct, or no, it's not, or?
Well, it is being used to basically know when do I have to coordinate or not. Because if your operations commute, and then I don't need to have coordination. I go CRDT way. Otherwise, I will need to add logs. So the idea is like, okay, you still don't see the merge, but now you have to define the invariants about how your data type behaves with concurrency, and then you let the algorithm behind the scenes that indeed you don't see because it's hidden for you. Yeah. So actually, maybe I could have explained this with that slide, because the idea is to translate this into something that you could put in your distributed key value store and then have it replicated. And the idea is that the distributed specification, we throw it into some tool, a static analysis tool. First version was dynamic, too slow, not performant. So we throw it to this tool that basically checks that we can generate the ICRO basically to properly serialize the operations to ensure the convergence. But it's not only ensuring that the replicas will converge, because this invariance is telling you about concurrency semantics, right? So basically, you could put there other kinds of invariance, not only for convergence. So what does the Ordana did? That's probably one of the crucial parts of ICROS, is that it will derive information about what are the commutative methods and how does it do that. Basically, you have the information here, right? So you have, oh, you see, sorry. So you had the information about what were the effects of the operation with the postconditions and what is the basically semantics that you want in phase of concurrency. So then what Ordana will do is to give you information about commutative methods. That was also like something that, for example, Carla had been done, also about conflicting methods, which ones not commute, and then it will find conflict-free solutions for the conflicts, and if not, if it couldn't find a solution for those conflicts by reordering the operations, then is when we lose logs. That was the idea. So you get this hybrid. So what is going on when you have an ICRO, after you get this ALDU set, that's an ICRO. You basically have object state, and your state is represented by the sequential data type. But there is the replication algorithm. And the replication algorithm will use the information at runtime of the static tool. So what we'll do is, like when you issue operations, it will construct a graph of operations, but it will append, for example, the happens before to keep the causality of operations when it does not commute, and it will also add these conflicts edges with information that it knows these two operations conflict. So then it will traverse this graph to find a serialization in which you don't have the conflicts. There were also arbitration, because sometimes you could not resolve, then both replicas had to take the same. It's very important that it's deterministic, because otherwise it will not ensure convergence. So I see that the thing is not here, the reference, but it's, I think, a couple of slides before. So I will not go over the algorithm. You can see it in the paper, because my goal was like, yeah, now we are getting closer. Oh, there is some strange thing going on here. Sorry about that. I will fix it for the PDF. Because now we can check, is this general purpose to build like basically application-specific RDTs. So we could implement the well-known CRDTs, some of them. Some things where we did not have CRDTs because you require coordination, but you can still use a stack and a queue. And then for certain operations, there will be the logs being put behind the scenes as a result of the Ordana analysis. And we could also build application-specific. This one is like some well-known benchmarking distributed databases that we use to basically compare that thanks to the static analysis, we could have less latency in some of the operations, because we could reorder, and then we didn't need the logs. And other people needed to put more logs because they could not do this reordering. So what did I learn here? Well, it is possible to augment these sequential data types with a distributed specification. We can go general purpose, but sometimes it will not be fully working without synchronization. Sometimes it will have to use logs. The static analysis was key to derive these efficient RDTs. The first version we will try in all possible serializations at runtime. It was terribly slow. And then based on this information, you could then use it at runtime to basically do try to run the operations without coordination. But if I'm a language designer, I see that I have a domain specific in Scala, but still it's a separate specification. What I am doing there is writing first order logic formulas, right? And actually, if you look at the specification already in that one of the LWT, here you have it, one word, yeah. As a programmer, it's stating the effects of an operation, but he might already basically written the operation. It has just said, okay, just add it to the sequential set. But you still need to specify in first order logic the effects, because we needed to feed it to the static analysis tool, right? The invariant is important, but if you look at this, if you want to provide or ease the development, it will be better that this will not have to be written by the programmer, because we need this to make happy Z3 in a certain sense, your static analysis tool, right? So, wait, let me go back. No, I went far too fast. So, no, went far too fast. This was the problem I was talking. Also subtle errors, because if you make some errors in these formulas, especially the post conditions, what will happen is that then the tool will not be able to derive that you could have a ordering of operations that did not require coordination. So then you may end up with having too many logs, or some runtime maybe anomaly. And then, of course, you have a specification that has to be run. So the DLS specification has to be maintained with the code. And that's where the idea came, okay, let's try to apply some language design. Could I have a high-level object-oriented programming language for the sequential data types, where I define the concurrent semantics, but it is within the same language? That's the idea. It's within the same language. I don't need to keep up with the two walls. And if you make it that it's fully compatible to SMT, then you could get these first-order logic specifications for free. But I still want to synthesize real data types that I can put in a key-value store in Scala, and that it works. Okay? And that's how basically we came to with Kevin, to the fx, what was language. So basically, fx is going to be a subset of Scala, and then you get pretty much inspired by it. Just that when you parse it to the ST, it will be used for two things. First, to analyze and to generate the SMT code that then will be fit to the analysis. So basically, the programmer will not have to write these post conditions, because this is, by doing an analysis here, it could be generated and then given to Ordana, because you really still need the information about the operations to have a efficient RDT. And the second one, it will basically go through a Scala plugin to a Scala program that then you will get the ICRO. So if we see now, it looks basically misleadingly Scala, because it is not full power Scala. Scala is very big, and not everything you can basically map it, or not everything we need it, you can map it to SMT, right? And behind the scenes, you know that there are these operations, the effects of this, they are being generated. So it looks like kind of a Scala, because it gives you as well like a set as a data type. It is based on functional, basically, kind of a functional way of operating with these data structures. And then you could annotate some class with replicated, and this annotation, basically what it will do is that it knows that this from here will have to generate an ICRO data type, and it expects that there are going to be invariants that have to be upheld. So if you want the add-win set, now you can add the invariant, in which an invariant for an operation that you have defined in the sequential data type, and then it check, in this case you do, this contains the element. So it's much more simplified, although in principle, behind the scenes, it is the same. It's just trying to hide some of the complexities to the programmer, basically. So if you wanted the remove widths, well then you change the invariant, but you don't need, you can still use the same trait, the same for the sequential part. Okay, so then fx could like get them from them. So how do we, Kevin validated this by trying to write the same portfolio of ICROs. It should be possible, right? Then it means that your translations to the SMT are correct, and then he added even more application specific besides the rubies. To basically did a bit of, I don't have time to go over the details, but it checked basically how easy it was then with the specifications. Go ahead.
Could you go back to the previous slide?
Yeah. Oops.
Why do you say it is really simpler than what you had before? Because you still have to do things?
Because now what I want is a general purpose RDT. I want to say when there are concurrent operations from different replicas, what do I do? So I need to maintain the invariant. But I don't need, as a programmer, to say what are the effects of after you do an add operation, what will be the effects on your program in the specification? Because you see it here. You see it on the code, on the body of your add. The effect of doing an add means that your set grows with one element. You already did in your implementation of the data type. But in the previous version, I had to implement it on the data type, but I had to write the specification to say what was going on.
But what is the purpose of this content? The question in the mic, sorry, so it's recorded.
Ah.
Okay,
I repeat the question, yeah. So the question of Manuel is that it's not understanding what is the invariant.
And what is the purpose of this content? Isn't it just checking the specification?
It's just checking that the element that you pass, it is contained in the set. So it's an AW set, and an AW set, basically, it's extending the trait of a set, and a set is just a regular sequential data type. So if you do an add of an element, your invariant, in this case, because the AND should win over any other concurrent operations that are happening, should be that after all the concurrent operations with the add, which could be a remove, which is the ones that don't commute, the element should still be contained on the set. That's what it says. This I cannot remove it because that's what makes that it says, how do you want your replicated data type to behave when you have concurrent updates? That I cannot remove. But everything about what is the effect of adding the element, which was before, I had to say, look, adding the element is putting it, and then I had to write it in first order logic. And I don't want that the programmer has to do that, right? So that's what it went away, because you have this language designed to then compile it to the first order logic. Yeah? Yes?
Why do we need the copy?
Well, yeah. So this is because it is expressed purely functional. So when you do an operation, it will give you a new data type with the effect. But in the first iteration, that was very inefficient. It was not done. It was done with mutation, and then we had the conjecture, maybe if it will be expressed as a pure functional, would give also better performance results. And that's why, and also because by then my PhD student got completely convinced that Scala is the best thing in the world. So, which I will say it is, because otherwise Mira maybe and other people here kill me. So that's why it is, this is expressed purely functionally. Yeah. Okay. Good. So we reached the end of this deal bin. Because then Kevin got even more ambitious. That was then him going more ambitious, because I was, wow, this is really cool. And then he's like, yeah, but Elisa, look at this. If I would be able to have like completely, that the language completely can be mapped to SMT, then I could basically have not only cross, because here we were generating the thing that goes to Ordana, but I could have correct replicated data types out of the box for the masses. That's what he called it, right? And that's where, when he put a lot of time into basically trying to have the maximum subset of Scala that have like the feel of a Scala. You have maps, sets, vectors, the list, so that you could have operations on this, as it will give more this functional favor, but that then it will be fully compatible with SMT, and we added one novel proof construct that basically that could express application-specific correctness properties. At the beginning, it was only for RDTs. So the idea was like, oh, now I can, without having to have a super deep knowledge on verification, because there is people that have done the proofs in the verification world by going the Coq way or the ACTA way. But what's our point was, we want to give tools to the programmer, so it should be easier for the distributed programmer, even if it doesn't have a deep knowledge on verification. And then, yeah, I mean, with this proof, it's like, yeah, then you could basically get automatic proof verification behind the scenes by discharging obligations onto the S&T solver. And that's what he did. The thing is, like, we didn't know when he started, it's like, how many CRDTs are you going to be able to do it in that way without basically only with the logics that S&T supports? It was not really clear, and we were surprised that of the amount of things that we could prove. Actually, I now see that I don't have the portfolio, but there are like about 50 CRDTs that have automatically proof, so you don't need to go into the cock, blah, blah, blah. But just by have them, you take the specification of Shapiro et al., for example, you put it in verifix, which is quite close to the specification, and then with encoding the proofs, they knew the proofs. The proofs are manual in the papers. We only encoded them there. You could get like a free verification. And this is where we are now. We are now into like exploring the possibilities of this iteratively workflow in which you design an RDT, you implement it in verifix, you get basically you have a trait for checking the state convergence, for the state-based CRDTs, for operation-based CRDTs, for deltas, for operation-based CRDTs, many of the families. And if it says correct, then you can transpile it again to Scala and deploy it to the system. And to deploy to the system, you basically need to give serialization. Again, the distributed semantics a bit. So by adding the serialization on the data type that comes here, he could put it into an existing distributed key-value store in Scala. If not, then you get, basically, that means that Z3 is complaining and gives you a counterexample. But that's not meaningful for your high-level programmer that doesn't know anything about first-order logic, yes, but not the complex logics of S&T solving. So basically what it does is that it expresses the counterexample in terms of the very fixed language so that you can then modify your implementation and then you can go here. We are still working on basically improving this workflow. It has been now like we had a summer school in September and there were like super surprising 6 other students who used the very fix to basically verify RDTs, but also for other kinds of proofs, because you could use it for something else. I will take your question. I finished the sentence. But I cannot say this because we are still have not tried all the power of the language. So for now, we can say what we have done with RDTs. Now your question.
Sure, and it might be related.
Yeah.
How difficult have you found it to interpret the counterexamples?
Oh. Yes, so he is asking how difficult, how difficult it is to interpret the counterexamples, correct?
I'm making an assumption here also that the programmer is the one who has to interpret the counterexample.
Yes.
That's not objective.
So before last year, only Kevin could. Because I was using it and for my classes, and I wanted to show the students what we were doing, and then I got this, and it's like, Kevin, I don't understand anything. You have to go through all this code and deep inside and the identifiers because it generated S&T code, right? So it was difficult. And then he added this that made my life much easier. But okay, there is basically an AST that it gets generated from the code, right? So, and he analyzes it to go to SMT. So basically he added support to go the other way around. But this is something that he did to please me, and because I thought it was essential as well to have users of the language. Which will bring me to the second part of the talk. So apparently, but the second one I will do it later. I know, I told you. So the thing is, like, this is very nice, but we are still exploring this, and you cannot use it for any distributed application. That will be my dream, right? But there are limits on what you can do automatically proof. And there are a lot of people working on theories to be added to SMT. There is a lot of people working on verification, like a la Koch and so on, where then you require the expertise. They can prove more things, of course, but I want something that is usable for the distributed programmer. So this is not yet there. That's why, well, what do I need to do? There will be failures, and I will need to complement this, basically, it goes beyond giving a programming model. I will need to provide tool support. I didn't need to wait till very fixed to know that, because basically tooling was essential when I started in 2007 to teach ambient talk. So, okay, Hadel Miller in the eCube was explaining all these war stories about supporting millions of Scala users. Well, I didn't have millions, but I had a bunch of master students and bachelor students doing thesis, going to the courses, who were using the language. And yeah, for the researchers, for me, with a text editor, and then I had the REPL. You cannot see the picture because it's all on raw resolution, but here there was limited syntax highlighting. A terminal with the REPL. The terminal didn't scare me from my C live, but apparently it scares a lot to people. And then what you see here is that this basically MacBook Air is talking to this phone and basically sending the hello. Sorry, the quality, it's an old picture. And yeah, the students were always saying that they found an error in ambient talk. And it was not true, it's just that we were not providing any tool support. And they could not also reason about all these distributed events and how it works. Of course I could do it, the interpreter was in my head, but not them, right? And the error messages were also not good. So even though, I mean, I was not developing the whole interpreter, but when you work in a project like this, you end up touching a bit everything. So I could help them, but without me, they were like always complaining. And then Android comes and you are teaching them with phones an extra level or source of problems, because with Android, well, if you have worked with it, there is a lot of, by then it goes at such a fast pace that every year they are a new release, the things that on that version doesn't work with that version. So it's like, let's give them our devices so that everything works nicely. They come with their own mobile phone because they are super rich and they all have mobile phones by then already. So then you have to account for all the hardware issues. So I realized pretty early in 2007 when I started teaching, this is not the way how to basically give a super cool programming model that Ambient Talk had on those for those days to users. So I started working within my PhD, another of this procrastination, about tools that allows them to reason about these distributed events. And I focus on debugging. So we had this programming model that we see, and it's again, okay, you have an error, so your intuition should be put a debugger, put a tool, and see what's going on. So try to understand. So the first work on debugging was basically not only giving access to the actors or the event loops and pause, but to have domain-specific features for the event nature. So when you pause and you want to step, you want to pause and step at the level of asynchronous messages. What we usually do in the debugging is that we have very good, we have debugging, very good, maybe debugging support for the sequential part of the code. But now I have as well the event-driven things, right? All these kinds of events. So, that was one thing. I want to pause and step at the level of messages. I want to put breakpoints, not in a source code line, but also for asynchronous messages. And it had to be epidemic because since we were in these mobile networks, I will start debugging one mobile phone, and at every mobile phone that will encounter and that will communicate, the debugging session will keep infecting the mobile phones that you were debugging. So it was a dynamic debugging session. It was not like, oh, I have a whole view of the distributed system. It will just do this epidemic. I also had something to browse the history of messages, but yeah, it's like no time. You need to write papers, so it was in a hidden button command line. Again, command line is not so bad, but yeah, they don't like it. So just super fast, we start looking into what are the breakpoints that make sense, and you do this by analyzing your event loop model, and then check oh, you can put it at sending or receiver side, and we started investigating what was. So, for example, one of the breakpoints I had in my debugger was that you could put a breakpoint on an asynchronous message, but actually you don't break the receiver, so in this case, the object shopping session that does the go, but I want to break when I get the result of the message. So even though you see the dot on an asynchronous message, who poses is the client code when you receive the answer. Once you were paused, you could also go then, it's like have a stepping again at the level of messages. So if you are paused here in this kind of, this was the shopping. So when you want to buy, you need to know that you have the part in stock. You need to check the credit and that you can deliver. So if I pause here, when I ship these 3 messages, I could step into and the 3 receivers will pause. And that I could investigate because the whole idea was like sometimes there were message interleavings between the actors because they were distributed, and I didn't know how that I end up into that state. So that was a way how to add online debugging, but at the level of the messages. And then it's like, how do I validate this? Well, yeah, let's do a user study. User studies are very hard, and this one is the first one I did. By now I have more experience, and I would do it differently. Of course, you will always try to do it differently. But we took the debugger to see if those features for the events were useful. And we did it with 22 participants who have done a master thesis or were doing a master thesis or had already had the course of ambient talk, because we needed that they will understand the ideas of ambient-oriented programming to then see if the tool will be valuable when you are a distributed programmer in that programming model. So what did I learn here? Well, they did value, because of course if you did not have a debugger that helped you to reason about all this, and now you had it, at least they value the tool. And you see this because this is the pretext before the experiment. This is the answers on the post-test. We have more positive answers on the post-test. And something that I particularly was pleasant, it was pleasant to see, is that the remedy debugger supported what they would expected that a debugger for a distributed programming language had to. So that was good, but they did not like it. The GUI was quick and hacked by me in Eclipse plugin. Neither the visualizations were up to date. The visualizations were still using the classical things that we use for sequential code, where you have lists of actors. This might not be the best way how to represent it. And basically it was pretty much list-based as how you would have it for a debugger in Visual Studio Code or for sequential code. So here we need to work more on this. And this brought me like then, it's like, okay, I did for distribution. But a bunch of questions come to me, like, how do I deal with the non-determinism? Because I couldn't deal with timing errors, right? I mean, if there was like errors that only happen because of certain timing conditions, was very difficult in an online way, how I had. How do I apply it to different ways? So, wait a second. The non-determinism also, it's important because of the non-reproducibility, right? If you put the debugger again, with the timing things, it might be that we will not get at the state that the bug will reproduce. That's hard. Then, to the different concurrency models is because basically it was like, okay, it has to be that you should be able to use the domain-specific things for distribution. Even if you are not using actors, you could still be using communication sequential processes, or you could be using other models like threads, but you should still, could we make it general, what I had learned? The visualizations, I had some students working on it because, again, we are not there yet. Another of the questions, like, could we build a debugger which will be proof effect free? So you know that, well, this is related to this effect with the haze and bugs, that just by the fact that you have an online debugger attached to an application, it could be that some scheduling of messages does not happen because the debugger affects the behavior, and then basically you could not reproduce. So could we make a debugger that did not have this, adding these extra proof effect things? How do we deal with big amounts of data, especially in distributed systems? And then again, remaining close to the hardware, can I put this in memory and network constraints? Okay, so I will do one delphine, but this one is shorter. Don't worry, I will finish on time. So let me drink again and do the last delphine. I don't know if there is any other thing in the meantime. Okay, so we go from PL to tool support. And I'm going to talk a bit about the work with my PhD student. By now, has a PhD, is earning big money in Nokia Bell Labs, which is about Hydra and SPA, and it's how to make online debugging practical for the big amounts of data. These are the systems that handle a big amounts of data, so that will be big data processing applications. Because what you see there is that, okay, you have long-running computation, so there is a huge, of course, volume of data, and it is distributed in the sense that they are always remotely executed on a cluster, and that also could slows down the debugging cycle if you have to connect there. And so there are many programming models, so we are not studying what is the best programming model here, whether with events, with data. That was not the thing. The thing is like when I get errors, how do I debug these applications? And the thing is like if when we started in 2016, there was this paper that said that 37 of the reported errors were related to developer. So if you look a bit, basically, you had things like code defects, so explicit errors inserted by developers, operation mistakes, like, for example, file renaming. This was more like dealing with the underlying, for example, distributed file share system, and also a lot of misuse, like configuration errors, because there is a big technologically different software stack, and sometimes it's very easy to misconfigure something. So by then, there were some debuggers, and well, there was a lot of logs. They take the logs, and then you had visualization on the logs, and then try to see what went wrong. But from the logs, you get very few contextual information sometimes, and they could not, took a long time to get what was the real reason from that the application failed. Second thing is like you had replay debuggers. So they will record. They were expensive, but they could record and then replay from the beginning. But since it's a long-lasting application, distributed system, you may have to wait like 8 hours of the replay until you could then start understanding, well, reproducing the bug. And then if you did not get it by the first run, you need to go again to replay from the beginning. So it was costly. But there was this paper, Big Debug, that was actually trying to improve this, and they will only replay from the last checkpoint. And then then I thought, this is interesting, but I want it a la Smalltalk. So those who are here that know Smalltalk, it has like this live debugging feel. Maybe there is nobody, they are all in the live program workshop. So basically, it's like, could we build a debugger that is online? So basically, you debug the system when the bug happens, because my goal is to basically avoid the replays. But it will have some, of course, domain-specific features for debugging. So like, it will give you a centralized view on what's going on with the different processes, all at the same time doing things on data. Hopefully, it doesn't interfere with the execution. And the interesting part is like then you can do as well updates of the running system, so you don't need to stop and then start everything, but that you could deploy code fixes to the individual workers where basically the error happened. So live code updating. And that's how we came to out-of-place debugging. So in Smalltalk, we said that that's an in-place debugger. It's always there in your system, but actually I want the capabilities of my Smalltalk debugger, but in another machine. Because I want to debug in the developer machine what is going on the workers without having to go remote debugging as how you usually will do. Right? So what it happened is that when there was an exception in the worker, it will wrap up a debugging session. It will send it to the master, and the master will serialize this and send it to the developer. And if you had another worker with exception, the master will be the one of coordinator. That's nice. You have infrastructure. It's a bit of like easier model than ambient talk because you can rely on the master as a point of communication with all the workers that are doing these functions with big amounts of data. And what's going on in the developer machine? Well, it is meant to be like in a small talk way. So a debugging session was nothing else than capture the execution state at a particular moment where the exception happened, and then reproducing it in the developer machine. And then there were a lot of other things, like for example, okay, remove the framework frames so that you serialize less data, because we are talking that these processes manipulate a lot of data. If you see that the session happens 3,000 times in the same worker, don't send 3,000 times sessions and the developer will be overwhelmed. But basically make a composite debugging session, one exception, and then see in all the records that fail. And then there were two strategies, because you are talking that you move the computation, but all your data where you are doing the processing is still in the server. So there we had here like taking the assumption is that when you will have errors many times, it was in the same partition. So you could move only the partition inducing the error. Okay, once you have this debugging session, it works as small talk, so you can be doing, in the IDE will record your changes. So you are debugging there, you can restart it if you need it. And then the code changes will be class modification, additions, refactories. It will be recorded there, and then it will compose a patch that you send to the master. And the master, it's good because, again, it has tools to know what is the appropriate time that you can interrupt these workers and push the batch to the workers. Now, as I said, there are many different programming models there. We only explored that idea with two. The first was for map reduce. Well, so this is like IDRA working on as an extension to Faro. And then basically you will get the composite exception. It had happened 3 times, so 3 workers had this exception that it said a reading number failed. And in this case, then you could have different strategies. Either you say debug all the failed ones, only the selected, or create me a virtual partition that looks like the one that is there when the error failed. We then also explore it in Spark. And in Spark, if you know a little bit about it, it works with replicated data structures. So then you also need dedicated stepping because you want to go to the next element that it's been added on that collection. So the next transformation that you do on an RDT or the next action. So it had dedicated domain-specific things targeted, in this case, for big data processing. And then it's like, this is very interesting. Are there other distributed systems that could benefit from a kind of a similar debugging so that we can reduce this latency of going and debugging always remotely so that we could do it locally to reduce the latency and to improve like the debugging experience? That's where we came to trying to apply these ideas, but for Internet of Things. They are not processing big amounts of data, but they are also event-driven. They also are deployed, basically, and if you need to debug remotely. Here it was a lot of log-based debugging as well. And many times, well, when we started, many times it will be only a remote debugger that you could connect serially. By now it's also wirelessly. And then we pair with the group of Christophe, which were building a virtual machine for embedded devices to build these Internet of Things applications on WebAssembly. So the idea was like, we have the programming model is there. We will basically just use like C, or you can use Rust. You write your application. You use the WebAssembly VM to have your code on the device. And could we improve the debugging of these systems by bringing out of place debugging? So actually the architecture looks similar, but now we don't have a cluster with masters and workers, but we have an embedded device. So in our case, most of the times we work with the M5 stick hardware, where it has the Arduino VM. And then basically it will have this debugger proxy. From the developer machine, what you would have is like the Visual Studio Code, where you have your source code. It will then go to WASM, and it will have the views. So basically what you see as well in the out-of-place debugger. But interestingly, there will be a VM locally, basically running the application with some monitoring. So the idea is that the first, initially, is like, no, I forgot there is one animation missing. So if you have here the code running on your microcontroller and you get an exception, a debugging session could be asked that will be brought into the front end, and it communicates with a virtual machine that is at the same status than it is there. So then you can debug locally while you have your remote device over there. So here it's a bit, requires not a direct applicability, because if you look at the source code of a NeoT application, you have basically location code that it's location independent, so it's doing some computation. But there are sometimes code that it's about non-transferable resources. We saw this a bit with the clouds, because the non-transferable resources were the data partitions. I couldn't take all the data from the cluster to my developer device. But here, basically, they were a different kind, because we were talking about sensor data, about buttons, about networking messages coming there. So then what we were doing with out-of-place debugging doesn't work entirely, or only in some circumstances, because what we did with Matteo is that you will always pool these devices, these resources, right? So you bring the partition to you. So if you have like an out-of-place debugger here, it means that when you hit something like read or switch on the left, or read the temperature sensor, you had to go to the device and say, hey, give me the reading of this device and bring it there. But in these cases, there are a lot of these resources that work in an event-driven way, right? I mean, if there is like a MQTT packet arriving here from somebody else that is talking to the device, this is not something that you can reproduce while you are debugging online and you go to the next line. The callback will never be called here because it arrives there. So that's where, with the students of Christophe, we thought we extended it, and they already had an event queue in the VM, and we exposed it to the debugging side. So basically, when there are events like networking, or some, if you push the button, what happens is that this proxy will bring it to the local developer machine, and then you could debug it. So basically what you are having is a kind of simulation environment, but it's not really simulated. It is real because it gets all the events from the device. The device is not doing computation because it is here in the debugging, but all the events that happen for real on the microcontroller gets forwarded and offered to the developer. We are still working on this, and actually some advertisement for him. You can learn more about debugging for his talk on tomorrow. And now I really reached the end, because I see that you are all getting tired and want to have some coffee, so don't worry. Because, well, I hope if there are 3 things that you remember from today, because I know that sometimes the Delft teams might be losing people, is that distributed systems are very successful, widespread. So it's not something that it was something very niche, or like when, like 20 years ago, it was a bit much more different than now. But they are still challenging to design and implement. So we are still working about, in the PL aspects, on how to ease the development. Because you cannot abstract the partial failures, that will never work. You cannot abstract the fact that there is no global clock that is shared. You cannot abstract the fact that they run at different speeds. So the characteristics of distributed systems makes that it is challenging. And my personal take is that it is essential to explore the programming abstractions together with the tools, basically, so that we give a full set of toolbooks to the distributed programmer. I just try to highlight you some of the work in this area that I did with myself or with my students. And actually, if you are interested in these topics, I'm working with collaborators for making happen the second version of the future of debugging techniques, hopefully next year in ECUP, as well as making the second version of the summer school on distributed and replicated environments, somewhere else, not the BUV. So that's it for me. I need to thank, of course, past current members of the group, as well as the main collaborators that I have since I lead the group. So this is a picture of us having some lunch and fun. Thank you. Yes, sure.
Do you have any questions?
Some thinking.
We need to have a question for the drinking pause. All right, just to start, I have a lot of questions, but you mentioned repeatedly a couple of times, probably like this, the challenges of working with the real constraints on memory and work when you are deploying in a distributed system. So could you elaborate, because it seemed like it's still an open problem on all of these stages of development. So where do we stand on there, and what can we do?
Okay, so I don't do research in the implementation techniques to make it faster. So I just can tell you about my experience as programming those systems. And many of the techniques that we develop sometimes are for, they are, let's say, the performance comes later. First, we develop the programming model, and depending on the target application, then the performance will come later. So it's the same in ambient talk. We were the same. And then when you go and you try to have it that it could be more than an academic, so that you can show the potential of the technology and you use the devices, here is where you encounter that maybe it doesn't scale your technique. So I'm not saying that everybody now has to go and start looking at scalability only, because we also need to have pure research about how to use the programming, but it is true that we still, there are techniques that we still cannot scale as how we would like. Even if you take, for example, the idea of the CRDTs is very, very interesting. But many times you have like assumptions of like fixed number of replicas that makes that the amount of data that you send over is restricted. And it is also interesting to keep always the line coming from the mobile networks, because there you don't have infrastructure, and then you go to a smaller devices, and it's like, okay, would my CRDT still work if I have a dynamic network? And it's working on not super low level, because we always try that we have a minimum VM. If you see, I mean, there are many people that work on Internet of Things systems that they go very low level, very constrained devices. We are not at this range, but an SP32 kind, what it is inside of the M5 stick, still is much more reduced than this computer or a cloud server. I mean, big magnitudes. That's also, and I think also because I have kept this interest as well, probably. My nerdy bit of doing these things with devices. And second, let's not lie, because I need to get funding. And if you look at industry, many of the people will not be on the most constrained, but they will be on the middle range, not full-fledged like this, but a cheap device, microcontroller that they can afford to put into their production, and that they basically allows them to package it as an Internet of Thing kind of thing. So now, that's why if you look here as well, we have people like Stefan or Tom's group. I work with the FVM people as well, because you need to work with them. Maybe there is another tandem. I want to have my super reflective language, whatever, but I also need to work with the people of VMs so that this is scalable. Does this answer your question? I went, I think, like, woo, woo. I went all over the place.
Yeah, that does answer the question. Thank you. Do we have other questions? You can, in fact, ask questions. This is a workshop, right?
They did ask some questions on their defense.
Yes. All right. At the last slide somewhere, you don't need to go there. This is a wonderful picture. But you mentioned that we need to explore novel programming constructs and abstractions and whatnot. So, so far, your entire story was, and then I had this idea, and then it worked wonderfully, and it did wonders, and then I had another idea, and it was also wonderful. So, did you have some?
Really?
Yes.
Did I found somebody who had a wonderful idea.
Sure.
I tried to implement it, and I found a bunch of problems to work on.
There were a lot of faces there. Sure. I'm not saying you claimed all the fame to yourself, but I do say that this all looked like a series of successes. So can you name maybe one idea that was really like, okay, this is a very attractive, novel concept that probably will totally work, and then it absolutely didn't?
Yeah, sure. I mean, of course, you want to show the success, but to reach there are a lot of attempts that fail. The C-cross algorithm had this idea of making a general purpose, starting with Bayou, all this. But yeah, we were serializing all the operations at runtime, as I said, and it was terribly slow because the more operations you get, you had a ever-growing graph of operations that you had to topologically sort. So it will never work out. Although how they look like, it was an extension to JavaScript. It looked more like the effects. So for the programmer, it looked nice, JavaScript objects, like a la JSON CRDTs of Clement. But then with this little invariant, it looked nice, but it was not performant. The E-cross, they are performant, but in my opinion, it looks ugly. Because you have this specification. So then you get into the success, if you want to call it, because you combine the best of the two worlds. That's one of the things. Other things that fail terribly. The out-of-place debugging, so keeping in this. We were trying to do it for production systems, and that was like really production systems, but not a la cloud. And that was not giving us like to have something where these features could really help. So we had to retarget. In a certain sense, it's like, okay, do we throw the idea, or is this something where it could be interesting, this kind of small talk-like debugging, but externally? And that's where we came to the data processing. But failures, there are a lot. So if maybe you were not paying attention to the dates, but I said that I started in 2005, but the paper, I mean, Ambient Talk is 2007, so it was like 3 attempts to get funding for a non-Flemish speaker to stay in Brussels. So I spent a lot of time trying to secure my funding. So in these times, I did all leasing work in Ambient Talk 1, which was thrown away because then we did Ambient Talk 2. So there are a lot of things that I have left in the drawer, or that they are not properly published, like exploring interrogative debugging for actors. It is a workshop paper, but if you don't have a user study, they don't want to publish it on anything serious like ICSI or whatever. So they are. but that's not what people like to listen sometimes. So by all means, my idea was not to say, oh, success after success, was more like to try maybe as well to inspire that sometimes you might have an idea. There is somebody who seems to solve your problem, and then you try to implementing, and then sometimes you can, you will need to adapt it, basically, and then you have a success. Sometimes you really need to work really hard because this super cool idea, it's very nice, but it does not work in practice. I don't know. That's my take.
Yeah.
So
Thank you very much.
Persist, please. If I would have stopped the first year, I wouldn't be here today.
Exactly. So the learning happens at the failures, and the successes are just monetized on that. All right. Last chance to ask questions. In that case, I close the session, and then we go to the coffee.
Yeah.
Thank you very much.
Thank you all.
Thank you.